Hey guys, welcome to Taking Action Chapter 1. I'm really excited that you're joining me for my very first digital PD. This chapter introduces us to the 8 effective mathematics teaching practices. So let's get started. This digital PD series is based on the book Taking Action, which explores 8 effective mathematics teaching practices. The 8 effective practices are based on 25 years of research and are backed by NCTM. These practices challenge our students to become thinkers and doers of mathematics. They support teachers in building students' conceptual understanding along with their procedural fluency. And research has shown that these practices do improve student learning of mathematics. So let's check out what these 8 practices are. The first practice is establishing mathematics goals to focus learning. Up next, implementing tasks that promote reasoning and problem solving. Building procedural fluency from conceptual understanding. Using and connecting mathematical representations. Facilitating meaningful mathematical discourse. Posing purposeful questions. Supporting productive struggle in learning mathematics. And last, eliciting and using evidence of student thinking. Each of these 8 effective practices work together to support student learning of mathematics. We're going to briefly discuss each of these practices in this digital PD course, but each of these practices are explored in depth in their corresponding digital PD course. So our purpose here today is just to become familiar with these practices. So let's get started with the first one. Our first effective practice is establishing mathematics goals to focus learning. Mathematics goals indicate what students are to learn and understand as a result of instruction. Our goals need to clearly identify what our students are to know and be able to do. Goals should describe the concepts, the ideas, or methods students will understand. And they must be clear and understandable to both teachers and students. We also need to consider how our learning goals relate to and build our students' understandings toward the rigor of our standards. And everything we say and do throughout instruction should be gauged against those learning goals. Goals should be used by teachers and students to help monitor progress. But the type of goal also determines the type and depth of learning students experience. So let's take a look at a couple of goals. The 2 goals we're going to compare align to this standard FBF 2.3, which is the standard that addresses transformation of functions. Take a moment and read through the standard, and then read through both of the goals. Pause the video if you need to, and press play to continue once you're done. Notice that both goals are the same because they both align to the standard, and they both deal with transformation of functions. However, there's a big difference between the 2. Goal 1 is very specific about what students are to know and be able to do. Goal 1 addresses the conceptual understanding of transformations. It requires students, first of all, to illustrate the different effects created by replacing a given function f of x with each of these. And students have to explain the effects that are created. The activities students would engage in for goal, for goal 1 helps them to see the relationship between the function equation and the changes that k causes to the graph. This is especially important for our students to see these kinds of things because we know they have misconceptions, especially when it comes to horizontal transformations. Goal 2, on the other hand, only focuses on the procedural. it is not clear whether students will gain a conceptual understanding from the learning that's identified in the second goal. So if I had to choose between these two goals, goal 1 is your man. Goal 2 is like a bad blind date. You don't know what you're going to get. All right, so up next is implementing tasks that promote reasoning and problem solving. These tasks are high-level tasks. The purpose of these tasks is to develop our students' conceptual understanding. We want to engage our students in opportunities where they have to think, reason, and make sense of a situation in order to solve it. These tasks need to be open-ended so that our students can use their own mathematical understandings in order to solve the problem. And learning is greatest in classrooms where the tasks consistently encourage high-level student thinking. When selecting these tasks, it's important for us to know our students' prior knowledge. The tasks we select should be doable for our students, yet still challenge them to think. Let's take a look at a couple of tasks to compare. Task A says you are trying to decide which of two smartphone plans would be better. Plan A charges a basic fee of $30 per month and 10 cents per text message. Plan B charges a basic fee of $50 per month and 5 cents per text message. How many text messages would you need to send per month for Plan B to be the better option? Explain your decision. Task B says to solve each of the following systems. First of all, let me say that both of these tasks have their place in mathematics learning. However, if we're going to consider which task has the potential for the greatest learning to take place, I think we'd agree that it would be Task A. Task A is a high-level task. If you notice, there's no specific pathway or method that's been suggested. So students can approach this problem using several different ways. They can use guess and check, they can make a table, they can graph the two equations and find points of intersection, or they can use algebra. In Task A, students have to put forth some effort in order to solve it. In contrast, though, Task B is a low-level task because it implies that students are to use a specific memorized procedure. So it's procedural practice only. The mathematics students learn by doing high-level tasks like Task A is very different from low-level tasks. Again, both of these types of tasks have their place, but it's Task A that's going to push our student learning. All right, let's take a look at our next effective practice, and that's building procedural fluency from conceptual understanding. Conceptual understanding is knowing why the mathematics work. Procedural fluency is knowing how the mathematics work. Effective mathematics teaching focuses on the development of both the conceptual understanding and the procedural fluency. So let's talk about a little bit more about what procedural fluency is. Fluency means students can choose flexibly among methods and strategies to solve contextual and mathematical problems. Students understand and are able to explain their approaches, and they're able to produce accurate answers efficiently. Both conceptual understanding and procedural fluency are essential and work together to support student learning in mathematics. So how do we build procedural fluency from that conceptual understanding? I'm glad you asked. Actually, we are going to explore that in detail in Chapter 4 of the Digital PD series. But I do want to give you a little sneak peek. So we're going to use a series of tasks and learning experiences to develop that procedural fluency from the conceptual understanding. We would start by developing conceptual understanding by building on students' informal knowledge. We would provide them experiences where they can engage only conceptually on the basis of their prior knowledge. Then we would give them opportunities to develop informal strategies to solve problems. This is where they can use what they know and what they understand and any shortcuts they know in order to solve the problem. The next experience would require them to refine those informal strategies to develop fluency with the standard methods and procedures. Then we'd give them opportunities to compare and contrast different methods to solve the same problem. That builds their fluency, but it also helps them to see the mathematical connections. And last, we would allow them to analyze worked examples to build their conceptual understanding. All right, next we have using and connecting mathematical representations. Effective mathematics teaching includes a strong focus on using different mathematical representations. And students who are able to represent, to discuss, and make those connections among these different mathematical ideas do demonstrate a deeper understanding, and they also have a stronger ability to solve problems. The types of representations we see in this figure, pictures, written symbols, oral language, real-world situations, manipulative models, the relationships and connections between those are bidirectional. And if students can understand these connections, then we've given them a broader and deeper understanding of mathematics. Helping our students see this connection is important. If they can see these connections, then they're able to make sense of different mathematical contexts. It also allows them to be able to recognize the connections among related mathematical concepts. And it sets them up to communicate mathematically. And if our students understand these connections and these relationships, they have a solid foundation for modeling. The effective practice of posing purposeful questions works to support mathematical discourse and prompt student thinking. So why is this so important? Asking the right questions reveals what students really understand about the mathematics. We can use questions to probe their thinking and encourage them to explain, elaborate, or clarify what they're thinking about. Asking questions also makes the mathematics more visible. And we can encourage our students, through our questions, we can encourage our students to reflect upon their own understandings and justify their reasoning. This will help reveal a deeper understanding in our students. And again, posing purposeful questions facilitates that mathematical discourse. So what kind of questions should we be asking our students? Things like, how did you get that? How do you know that? Can you explain your idea? Why? Can you convince us? Did anyone get something different? Can someone tell me or share with me another way? Do you think that means the same thing? Is there another opinion about this? And why did you say that? So purposeful questions and meaningful mathematical discourse go hand in hand. So our next effective practice is facilitating mathematical discourse. It's important for our students to be able to talk about the mathematics. When students can talk about the mathematics to each other, it gives them an opportunity to share their ideas and clarify their understandings. Giving them a chance to develop arguments to defend their solutions further cements their understanding. And having these discussions in the whole class gives them opportunities to hear different perspectives from other students and think, hey, I didn't think of it that way. We can also use mathematical discourse to help them link the new learning to prior knowledge. And it engages our students in the learning process. And one of the big things about mathematical discourse is that it advances the mathematical learning of the whole class. And it also helps to build our students' confidence that they can do math. So as teachers, we have a few tools that will help us generate mathematical discourse. We can facilitate math talk in our class by, first of all, revoicing what students have said. For example, so you are saying that blank. Do I have that right? Asking students to repeat or restate what another student just said is another tactic we can use. We can ask our students to explain their reasoning or if they agree or disagree with another student and why. Inviting students to add on to the conversation is also important. And another important tactic is waiting. Giving students the time and the feeling that it's okay to take their time to think through before responding is important. And last, we can have our students turn and talk or think, pair, share. This gives them opportunities to talk to one another again and clarify those understandings or hear different ideas. Giving students these opportunities solidifies what they understand about the math. But it does require us teachers to be proactive in facilitating and in anticipating where that discourse should be directed. And you also have to have solid classroom management. Our next effective practice is supporting productive struggle in mathematics learning. Productive struggle is absolutely necessary in developing student conceptual understanding. Productive struggle requires students to work and make sense of situations and determine a course of action to take when that solution strategy is not obvious or implied. Tasks that promote reasoning and problem solving support productive struggle. However, such tasks need to be doable for our students, while they still present enough of a challenge so there's something new they have to figure out. But what does productive struggle look like? And what does it not look like? Productive struggle should lead our students to understanding the mathematics. That's our whole goal. It should make the learning goals feel like they're doable. Productive struggle should yield viable results. And our students should feel empowered in their learning. They should feel like, yes, I can do math. Productive struggle, even though it's challenging, should create a sense of hope in our students. And like I said earlier, it's absolutely necessary in building our students' conceptual understanding. And we can use it to build their confidence. Now let's talk about destructive struggle. Destructive struggle leads our students to constant frustration. In destructive struggle, the learning goals feel hazy or out of reach, something they can't do. Students end up feeling hopeless and fruitless. They feel abandoned and on their own, and they feel inadequate. So productive struggle is what we want our students to engage in, not destructive struggle. So when we implement tasks that promote reasoning and problem solving, or any mathematics activity in our lessons, we need to make sure we're supporting our students with the resources and the instruction that makes them feel confident that even though this is tough, even though this is hard and it's a struggle, that I can get through this. And we also need to set a culture in our classrooms where students understand that they will struggle, but that it's okay to struggle. And the 8th effective teaching practice is eliciting and using evidence of student thinking. This provides us teachers a window into what students are actually understanding about the mathematics. It makes visible what students actually know and what they understand. And it allows us teachers to make decisions in real time during a lesson, as well as how we can adjust future lessons based on what our students understand. All 8 of the effective teaching practices work together to support student learning of mathematics. And again, the purpose of this course was just to have a cursory introduction to each of these practices. We will explore these further in their corresponding digital PD course. So thank you for joining me for this digital PD. Be sure to complete your assignments in a timely manner. Start by reading Chapter 1, Setting the Stage. You will have 3 assignments to complete. Assignment 1 is a teaching practices questionnaire. Assignment 2 is a required reading, followed by an actual questionnaire. So assignment 2 has 2 parts. It has the required reading, followed by a questionnaire. And assignment 3 is your discussion forum. So make sure you post your discussion to the forum and then complete the forum verification. Well, thank you for joining me for the Chapter 1 Digital PD. If you should have any questions or issues, please shoot me an email. I hope you join me for another Digital PD.